and most awesome distribution in all of statistics. It's also, in a way, the very most basic distribution. So in a way, it's super cool and powerful, and in a way, it's like the analog of the equation of a line or something. It just happens everywhere. So the distribution we're talking about today has a very boring name. It's called the normal distribution. And I want to show you why it's so important. So I got some data here plotted up here. I've got the head length of a sample set of possums. Who cares? I don't know. It's just some random data set. So what I want you to notice about the data set is that it's unimodal. It has one large bulge here. It's fairly symmetric left and right. And it has these tails, right? This part over here is called the right tail of the distribution. And this part over here is the left tail of the distribution. These correspond to the possums that, for whatever reason, have shorter heads. And these correspond to the possums that have longer heads for whatever reason. This is an entirely typical and normal distribution. And what I want you to note about the thing is its general shape, okay? So it has this basic bell shape. This shape is entirely typical of all kinds of naturally occurring distributions. Nothing special about possums. It's really something special about the way data tends to behave. It tends to be clustered in the center, with some exceptions out here. We have a central bulge, we have a right tail, we have a left tail. Normally, data tends to be kind of symmetric like this. So this is just what's typical of data. Now here's just a completely random data set. This is the attack rating, whatever that means, of 800 different Pokemon. Now it's a little bit different. It's a little bit asymmetrical. It kind of leans out to the left a little bit, but it's basically the same general shape. One large bulge in the middle. We got a right tail, we got a left tail. That's very typical. Here's another typical data set. This is the resting pulse of 362 people. Is there something special about pulse? No, there's something special about data that tends to make it keep looking this way. One large bulge and tails along the outside. And then here's the yardage. That's how many yards of progress down the field the home team made in football games in 2011. Is there something special about football? No, there's something special about data. Data just tends to look in this particular way with one large bulge, tail on the right, tail on the left. Now, what you've got here is 4 different example distributions, and the histograms show you where the actual data lies. But this blue line is plotted on each, and that is kind of a general model of how frequently those data values occur. Values between 90 and 95 in this data set are very common, and this blue line is very tall. Values around 100, 105 are very rare, and this blue line is really rather short, okay? So we have this blue line here, which records roughly how common these kinds of data values are. And in each of these graphs, the possums, the Pokemon, the pulse, and the yardage, the blue line illustrates how commonly those values are actually occurring. And I've also plotted an orange line on there. That orange line is a model or approximation for the blue line called the normal distribution. In this case, the normal distribution is centered at about 92, and it has a standard deviation, which looks to be about 5 units one way or another. In this case, the normal distribution is centered at around 80 and seems to have a standard deviation, maybe 20 or 30 units each direction. Here we have a normal distribution plotted in orange, whose center is about 70 and whose standard deviation is about 10 or 20. And here in orange, we have a normal distribution whose center is about 350. So the mean there is 350 and the standard deviation is maybe 50 to 100 units. The important thing to notice is that the normal distribution is actually the perfect shape of a bell curve, and it really rather closely models the blue in each of these examples. See how close the orange and blue are, how close they are, how close they are, and again, how close the orange and blue are. This is just natural data that's occurring in the wild, but it's very, very closely modeled by the normal distribution. That means that the normal distribution is a kind of a standard against which data distributions can be judged. And many data distributions are very, very close to the normal distribution. And that means that if we can understand the normal distribution, then we kind of have a generic understanding of how all data should look, at least normal data sets, well, usual data sets, I should say. So here's a picture of the literal perfect normal distribution. It has this fancy equation, but you don't have to know the equation right now. 1 over s times the square root of 2 pi times this crazy thing. Now, this formula is some crazy formula for this graph, and it has an m in it. I would use a mu instead of an m, but Desmos is an app that doesn't like Greek letters so much, so I used an M for mean. It has an M in it for the mean, and it has an S in it. The S represents the standard deviation. And if I set the values of M and S with these sliders, then I get various shaped normal distributions as appeared in these kinds of diagrams over here. Now, if I change the mean, then the whole thing will move right and left. If the mean is 4, then the thing will be centered here at x equals 4. If I change the standard deviation, what you'll notice here is that the graph goes up and down. But that's not really the right or the important interpretation of what's going on here when the standard deviation change. What's really happening with the standard deviation is the standard deviation is a measurement of spread. When the standard deviation is larger, the graph is more spread out. So here, the graph is spread out more broadly along the x-axis. And as a consequence, it happens to be shorter. So here, taller is not the point. The point is that the data is squeezed more tightly into these regions. Here, the region, roughly speaking, between 3 and 5, it's squeezed very tightly within that region, and therefore this graph ends up looking taller. So normal distributions vary in their mean because they can be centered at different locations. They vary in their standard deviations because they can have various levels of spread. But they don't, other than that, vary in any sense at all. They are otherwise exactly the same. So any two normal distributions with a mean of exactly 3 and a standard deviation of exactly 2.5, any normal distribution with that data will look like this. In fact, one interpretation of the normal distribution is it's the distribution you get if the only thing you know is you have the mean and you have the standard deviation and you try to make a distribution. If you have data about the mean, which tells you where it's supposed to be centered, and data about the standard distribution, the standard deviation, which tells you how much spread you're supposed to get, and you know nothing else, then your best guess for what that distribution should look like will be the normal distribution. So what's so special about the normal distribution? Well, it's typical. It's a good model of all distributions. Another thing that's special about the normal distribution is it's the distribution which exactly matches this rule we've called the empirical rule or the 68, 95, 99, 7 rule. For the normal distribution, these approximations that we've talked about in the past are exactly true. That is exactly up to the rounding. These numbers are slightly rounded off. So for the normal distribution, this data is exactly true, that exactly 68% of the data will necessarily lie within exactly 1 standard deviation of the mean, and exactly 95 will lie between 2 standard deviations of the mean, and 99.7 will lie within 3 standard deviations of the mean. We've seen in the past that these are good rules of thumb which apply to various distributions with approximate success, but for the normal distribution, then they will apply perfectly in the sense that it really is 68% lying between exactly 1 standard deviation below and above the mean. So the 68, 99, 95, 99, 7 rule applies perfectly to the normal distribution. What else is important to us about the normal distribution? It's predictable. The normal distribution behaves a certain way, and you can count on it to always behave that way. So if you have a normal distribution here and you want to say, gosh, my data is 1 standard deviation from the mean, then you might want to ask yourself, how strange is that? How unusual is that? How much of a normal distribution would lie 1 or more standard deviations from the mean? In that case, what you're really asking here is how big is this tail? How much of this data will lie out here in the right tail? Now, if you have just any distribution, I don't know. It could be a quarter of the data. It could be a tenth of the data. It could be whatever. I don't know. But if you know something about the distribution that it's normal, then these questions have predictable answers. And you can say definitively, in this case, just about exactly 15.8% of the data will lie in that region, in that zone, 1 standard deviation above the mean or more. And so that gives you a certain predictability, which is extremely useful when we're trying to figure out the results of our hypothesis tests. So the normal distribution is the simplest distribution in statistics, but also by far the most important distribution in statistics. It is a very, very good, eerily good model for real data in many very common situations. And therefore, we can use our knowledge of the normal distribution to answer questions that otherwise would be completely unanswerable.